Okay, so I think we'll get started. So what we'll do is, I shouldn't have told people that this wasn't going to be tested. I guess maybe I'll reverse my decision and put this on here. All right, so what we're going to do is we're going to talk about polarization to start. And the idea is fairly straightforward. And so the starting point is to think about a neutral atom first in zero electric field and then in a non-zero electric field. So in an electric field. So our neutral atom is going to have some nucleus, which is positive. So how many did I draw there? 6. And it'll be surrounded by an electron cloud. And so the electrons will be more or less uniformly distributed around that positive nucleus. And so this is the case where E is equal to 0. Okay, and then what we're going to do is we're going to take that same neutral atom and we're going to put it in an electric field that's not equal to 0. So what will happen is we'll have our nucleus with 6 plus charges, something like that. But now this electric field is going to exert forces on these light electrons, and it tends to displace them down a little bit. It'll also exert forces on the nucleus, but the nucleus is typically very heavy compared to the electrons, and so most of the displacement is due to displacement of the electrons. And so you end up getting this kind of distortion of the electron cloud, where we're going to have a higher probability of finding charges, say, displaced in the direction opposite of the electric field. And then what we can do is we can model that as kind of like this little pill where on average, there's more positive charge near the top end than negative charge. And so this little separation of charge, we're going to define like a dipole moment for this separation of charge. And, we can associate with this some kind of distance between the positive and negative charge. Now, we're not going to be interested in individual atoms per se, but like a material that's made up of a large collection of these neutral atoms. And then we put that material in an electric field, and all of the atoms get this sort of effect. And so they combine to make a large macroscopic effect that we can observe in these materials in an electric field. Now, that's not the only mechanism to get these polarized materials. You could also have molecules that are inherently polarized. Water is the prime example. So polar molecules in an electric field. Okay, so if we had like a cup of water in no electric field, water molecules are all polar, but they would tend to be in these random directions and there would be no net macroscopic effect. But now we imagine turning on an electric field and let's see what would happen to our water molecules. So we have oxygen and then 2 hydrogens. I think, what's the angle between them? Like 105 degrees or something like that. So this is our hydrogen, H2, and then we have our O. So there's our oxygen. And now what we're going to do is we're going to put this, say, in a horizontal electric field, for example. And so I could model my polar water molecule as something that has sort of a center, and then it's got some positive on one side, and then it's got some negative on the other side. And if it's inside this electric field, the positive end is going to feel a force in the direction of the electric field. So this is some force. And then the negative is going to feel a force in the opposite direction. And then there's going to be a torque on this polar molecule. That torque is going to tend to align the positive end in the direction of the electric field and the negative end in the opposite direction. So again, if I got my cup of polar water molecules and I put them in a strong external electric field, they're all going to rotate to make that alignment. And we're going to have some, on average, positive charge pointing, say, up if we have a vertical electric field, and negative charge, the negative ends pointing down. So in either case of neutral atoms or polar molecules, we get a separation of charge when placed in an electric field. And what we're going to try to do is we're going to try to work out some of the effects that these materials possess when that situation arises. In order to do that, what we'll first do is we'll first work out some properties of the electric dipole. So the electric dipole. In fact, the main thing we're going to do is we're going to write down the potential of the electric dipole. So the electric dipole, physically what it is we have some positive charge plus Q separated from some equal but opposite charge minus Q. Oops, let me move that over, get it lined up. Okay, and then we're going to say that that separation distance is D. Okay, and we're going to be interested in what is the potential over at some point P, maybe sitting over here. And let's see if I can connect this. There we go. I'm going to call script R plus as the vector from the positive charge to point P. And we'll have script R minus as the vector from the negative charge to P. And then from the midpoint, I will make script vector R without a subscript. And so the distance here is D by 2, and this is D by 2. And this angle between vertical and script R is going to be theta. So writing down the potential is a fairly straightforward thing. We know how to write down the potential of a point charge. It's just 1 over 4 pi epsilon naught Q divided by the distance. And so we do that for both of them and then add them up. But what we're going to do is we're going to make some approximations. So the exact potential, the potential at P is 1 over 4 pi epsilon naught. And then we have the positive charge divided by its distance to P. And then we have the negative charge divided by its distance. Okay. Now, what we're going to do is we're going to make an approximation for this R plus and R minus in terms of the R without the subscript. And this approximation is going to be valid when P is far away from this electric dipole. So specifically, say script R is much bigger than D. So let's find the potential at P when script R is much bigger than D. And so this might be called the far field case. So the fields far away from the source of those fields. All right. So to begin, what we'll do is we'll use the cosine law to relate R plus to R. So R plus is going to be equal to, we won't make any approximations yet. R plus is going to be the square root of, let's see, it's going to be script R squared plus d by 2 squared. So if it was a right angle triangle, we would be done. But then we would have -2 times the products of those distances. But we have a d by 2, so that cancels the 2. So we get minus d times r times cos theta. So that's cosine law. All right. We'll start by factoring out the script r. So again, there's no approximations yet. This is still exact. So it'd be 1 plus d over 2r squared minus d over r cos theta. Okay, and so now we will make an approximation. So if d over r is much less than 1, we can ignore the d over r squared term compared to the d over r to the first power term. Okay, so then, in fact, what I'm really going to care about is the inverse of all of this. So we're going to get 1 over r, first of all. And so let me make this an approximately. And then we're going to get 1 minus, let's see, d over r cos theta to the -1/2. Okay, so I've dropped that term. I want to make another approximation, and it's my favorite approximation because seems to come up all the time. We're going to use the binomial approximation, which says that 1 plus, let's say, x to the power p is approximately 1 plus px when x is small. All right, and so we should satisfy this. The cosine is some number between plus and -1, so it never gets very big, but it multiplies d over r, which we're assuming is small. So this 1 over r plus is approximately 1 over r. That doesn't change, but then we're going to get 1, and let's see, p times x. P is -1/2, and x is minus d over r cos theta. So we get plus d over 2r cos theta. Okay, I think that looks right. You could do the exact same game for the r minus, and what you would find is something very similar. It's going to be 1 over r. It's just going to be a 1 minus d over 2r cos theta. Okay, so what we're going to do is we're going to take those approximations and put them into our exact potential above. And so therefore, what we're going to get is V is, I could factor out the Q. It's Q over 4 pi epsilon naught. And then let's see, we're going to get 1, well, okay, we'll just write it out. 1 plus d over 2r cos theta. That's 1 over r plus, and then we get -1 minus d over 2r cos theta, like so. The ones will cancel, and the other terms will end up adding. So we get rid of the 1/2. And so our potential V is going to be approximately Q times D times cos theta over 4 pi epsilon naught, and then just a script R. And
And I think it should be, I have a squared for some reason. Did I screw something up here? Oh, sorry. Yeah, I forgot the 1 over r's that are out front. So that would sit there, and this would be a square. Good.
So that makes sense, that d is length and 1 over r squared is length squared, and we need a 1 over length.
So there we go. That's better. All right. So what I'm going to do is I'm going to go back to our original picture here. Where did it go? Here it is. And I'm going to define a vector that is going to go from the negative charge to the positive charge. And I'm going to call that vector P. And it's going to be Q times D. And let me also label here r hat unit vector.
So then, if I was to take p dot r hat, it's going to be qd cos theta.
Which is exactly what we had in that potential. So if we define P is equal to Q times D, then P times R hat is QD cos theta, which is exactly what we have in the numerator of our potential. And we would say V is equal to P dot R hat over 4 pi epsilon naught r squared, and P is called
The dipole moment.
P is the dipole moment. Okay, good. So that's essentially the one thing that we need in order to discuss our polarized materials. It's going to be the launching point for our discussion of materials immersed in an electric field. Okay, so in an insulator or dielectric, in an electric field, we can get a large collection of small dipoles that collectively can have a large effect. A simple example is to take two capacitors, a capacitor. It makes a uniform electric field, and let's put an insulator in between the plates of that capacitor. If we did that, what we would effectively have is here's our insulator, and I will say this E0 is the electric field that the capacitor produced in the absence of that insulating material. When we stick that insulating material in there, we end up getting all these little dipoles. And so I'll draw a bunch of them. Okay, so let's see, I can put a few more in here. Plus minus, plus minus, plus minus. All right, good. So there's our polarized piece of dielectric material. So the material becomes polarized. And the polarization is, so this is a capital P, is going to be the dipole moment per unit volume. So this is dipole moment, which is little p per unit volume. All right. So what we could do is we could take a small little volume in here, say d tau. And if we were, for example, given the polarization of that material, and we took that polarization, multiply it by d tau, that should be equal to the dipole moment inside that volume, which might be due to like a small collection of these atoms that are polarized due to the external electric field. But if you look at this picture, if you look at the inside, you know, wherever I have a negative, I have a nearby positive. And so here's a positive and a negative. And so those tend to cancel out. But what won't cancel out is the fact that we've got this kind of collection of positive charge near the top and a collection of negative charge near the bottom. And so if you have that separation of charge, it's going to create its own electric field. And our first goal is going to be to try to calculate the electric field due to the polarized object itself. So not the electric field that caused the polarization, but the electric field that arises because of the polarization. Okay, so the polarized object will create its own electric fields to calculate E. We're going to start with the potential V. That's why we went through the trouble of writing down the potential of a single electric dipole. Okay, so for a single dipole, we know that V is at P dot R hat 1 over 4 pi epsilon naught R squared. All right, so for a volume element d tau, we'll say d tau prime inside our material. The dipole moment is the polarization times d tau prime. In fact, let me be explicit. This is going to be something like so. So R prime is going to be the vector from the source to the field point, and the source is just wherever our little element d tau is. All right, and so we're just going to stick that into our potential for our dipole, and so we say therefore the potential integrated over all the d taus that make up our entire volume is going to be this volume integral of the polarization dotted with R hat over R squared d tau prime. And so in principle, we could just stop here and say, look, that's the solution. You just have to do this complicated integral every time you want to calculate that potential. And then if you want to know the electric field, you would take the gradient or minus the gradient of that potential to get the electric field. But what we're going to do is we're going to try to re-express this potential in a way that will kind of be a little more revealing to what's happening in these materials. So we want to re-express number sign in a more convenient or revealing, in a more revealing form. Okay, so the starting point is to make the following note. So note that Okay, so what does this mean? This means I'm going to take the gradient, but with respect to the primed coordinates of script r. So remember, script r is r without a prime minus r with a prime. And so we're going to try to evaluate this derivative. And what my claim is that this is going to be equal to r hat over r squared. If that's true, then I can make this replacement in here, and then we can do some manipulations. You can kind of see that we're going to get some gradients in a volume integral. That kind of looks like divergence theorem, and that might help us. Okay, so let's just first evaluate the x component of this derivative. So when I take the gradient, I'm going to have the x component is going to be this x prime derivative of 1 over r. Now, 1 over r is going to be x minus x prime squared plus y minus y prime squared plus z minus z prime squared. We'd have to take the square root and then take the inverse. So I'll put it all to the minus 1/2 to get the 1 over r. All right. So when we evaluate that derivative, we're going to get a minus 1/2 of, let's see, all the stuff that was in the square bracket to the 3/2 in the denominator. So I won't write it all out, but it's all the stuff that was in there. And then we have to take the x prime derivative here. We're going to get a minus 2x prime. So this is going to be minus 2. So actually, sorry, I should be careful. It's minus 2 of x minus x prime. And so the minus 1/2 and the minus 2 cancel, we get x minus x prime. But all of this stuff is 1 over script r to the power 3. And so we end up getting x minus x prime over script r cubed. If you did this for the y component and the z component, you'd get terms just like this. You'd get an x hat here plus the y term with the y hat plus the z term with the z hat. But then this x hat plus the y times the y hat plus the z times the z hat. That's just script r. And so with all 3 components, we would find that this gradient of 1 over r with respect to the prime coordinates would be vector r over r cubed, which is the same thing as r hat over r squared. Okay, so that's fine. So what we're going to do is we're going to go back to number sign, and we're going to replace our r hat over r squared with this gradient. Okay, so therefore we can write number sign as, well, let's see. 1 over 4 pi epsilon naught, that doesn't change. We still have a volume integral. It was this polarization dot product. Now, here's where the change comes in. And then this is a d tau prime. All right. Before we get to the divergence theorem, we have to do some gymnastics with a product rule. So product rule 5 from the front cover of Griffiths says that this dot product of the gradients can be expressed as, let's see, I don't have these memorized. It's the divergence of the polarization over R. That's the one that's going to lead to divergence theorem minus 1 over R times divergence of the polarization. Okay. So what does our potential become? there's going to be two terms now. So we get the one where we're going to be doing divergence theorem. And then it's 1 over script r. And we could close our bracket. Okay, good. So here we apply, whoops, apply divergence theorem. Okay. So 1 over 4 pi epsilon naught. What does divergence theorem say? So our volume integral is going to become an integral over the surface that bounds that volume of p over script r dot dA prime. Okay, and then minus 1 over 4 pi epsilon naught, the integral of the divergence of p over script r. This one, I'm not changing anything. I'm just going to leave it as it is. All right, so what I want to do is I want to try to convince you that these two terms are somewhat familiar. Okay, so what I want to do is I want to compare the first term to 1 over 4 pi epsilon naught, the integral of sigma over r dA prime. This is something we calculated, I think probably back in chapter 3, maybe. This is the potential due to a surface that carries surface charge sigma. So everything's the same except the P and the sigma. So in fact, it's a P dot dA prime and a sigma dA prime. So if we can somehow associate this P with a surface charge, then that might lead to something that's a little more revealing. And then let's look at this one over here. We want to compare that one to 1 over 4 pi epsilon naught, where we had a charge per unit volume divided by script r d tau prime. And so what we're going to do is we're going to associate this divergence of the polarization with the minus sign as a charge density. And then all of the apparatus that we used for calculating, say, electric fields from surface charges or volume charges can then be applied to these polarized objects. Okay, so let's start with this one. This one's a little easier. So we can associate this minus the divergence of the polarization. And I'm going to drop, I'll drop the prime. So let's drop the primes at this point as what people call a bound charge density. So this is a bound volume charge density. And let's just emphasize right off the bat that this is non-zero only when P, the polarization, is not uniform. Because we need a non-zero divergence for this to be a non-zero rho B. All right. So if we think of this dA prime, usually when we had these surfaces, so let's see if I can draw some kind of funny looking Cheeto type surface. Remember, we defined these normal vectors that pointed outwards from the surface. So what we can do is we can say that if we take the polarization dot n hat, so if this is like our dA, dA is equal to dA n hat. So I'm going to separate out the n hat, and instead of writing dA as a vector, which I shouldn't have done here, this doesn't make sense. Get rid of that vector. What I want to do is I'm going to write this dA prime as dA prime scalar times n hat, and then p dot n hat is what we're going to associate with this sigma. And that's going to be defined as sigma b. And so this is a bound surface charge. All right. So with all of that in mind, then our potential becomes 1 over 4 pi epsilon naught, the integral over some surface of the bound surface charge divided by r plus a term for the bound charge density divided by r with a d tau prime. The sigma b is fairly easy to understand its origin, and it's related to what we already drew. If I take my polarized slab that's between the plates of a capacitor, draw a bunch of these polarized, say, neutral atoms that make up whatever this material is, Teflon or something like that. Then we end up with, like we said before, a lot of these positives end up canceling with interior negative charges, but you end up with some positive surface charge here and some negative surface charge over here. So this would be negative sigma b. So that's that bound surface charge. I've kind of drawn something that's uniformly polarized, so it has no divergence. And so this example would have no rho b. But if you had some complicated electric field where you were pushing, I don't know, charges were polarized in some weird way where the positives were kind of out on a sphere, then you would have this divergence, which is non-zero, and you'd have a collection of, say, negative charge in the center pointing out to some positive charge, and that would be like a bound interior charge. Okay, so this is roughly equivalent to just some concentration of positive charge near this top surface and negative charge near the bottom surface. And this would be due to some external field causes that polarization. And the result is that you get an electric field that's due to, say, the bound charges or the polarized object. Okay, so that's the idea. That's the basic idea. Let's do an example. Okay, so example. We want to find the electric field due to a uniformly polarized slab. So this is just the example that we were already talking about. So if I say uniformly polarized, right away, what you should be thinking is if P is uniform, it has zero divergence, there's no bound surface charge, no bound charge density. Okay, so we could say since P is given as uniform, that implies that rho B, which is minus the divergence of P, is equal to 0. Okay, so we'll take our slab here, like so, and we'll say it's uniformly polarized. So P is
Like so, I mean, I'm drawing only one P vector, but it's uniform everywhere.
P is the same no matter where you are in this slab. Okay, then, well, let's see. N hat are these vectors that point outwards from our surface. So at the top, N hat points up, and at the bottom, N hat points down. Okay, and so that means sigma B, which was P dot N hat. Let's do the top. Well, that's just going to be P times, say, Z hat dot Z hat, if we call this the Z axis. And so at the top, the bound surface charge is just equal to P, the polarization. And so that's positive, and so we get this positive charge at the top. And so at the bottom, sigma B is going to be P dot N hat, which is going to be P Z hat dotted with minus Z hat. And that's just going to be minus P. And so what we end up with is a bound surface charge at minus. So, sorry, let me fix this. This would be sigma B is equal to minus P, and this is sigma P is equal to plus P. All right. So we're going to try to find the electric field due to this. But we already know how to calculate electric fields for a sheet of charge. What would you do if you had a sheet of charge and you wanted to know the electric field? What tool would you use to find that? Gauss's law. Does anyone remember what the answer is? So we, yeah, sigma over, did you say over 2 epsilon naught? Yeah, that's right. So we know that for a sheet of charge, yeah, that's right. So we've essentially made a capacitor of bound charge. Like the material itself is neutral. We've just polarized it so that there's a collection of positive charge at the top and a collection of negative charge at the bottom. And so it's like a capacitor, and the electric field that we get is exactly the electric field of a capacitor. So in fact, what we could do is we could say for the negative charge, we're going to get an electric field here that would be pointing towards the negative charge, and it would have a value of E is equal to sigma B over 2 epsilon naught. And between the plates would be sigma B over 2 epsilon naught. Above the plates, it would be sigma B over 2 epsilon naught. But then we also have the contribution from the positive surface charge. And electric fields point away from that positive surface charge. And so just like a capacitor, what we end up with are electric fields that add between the plates and cancel outside of that plates, or outside the surfaces, or outside the material in this case. So we end up with E is equal to minus P over epsilon naught Z hat. Let's say, I guess I should just say minus P over epsilon naught inside. Right, so notice that the electric field is in the opposite direction of the polarization in this case. And if you add these up, you get sigma B over epsilon naught, but sigma B is just equal to the polarization. And then we get 0 outside. Okay, good. the next thing I want to do is I just want to just do a little exercise to confirm that our polarized object is always going to be neutral. If we start with a neutral object, place it in an electric field, it gets polarized, maybe it has a sigma b and a rho b, but overall it should be neutral. Like all we're doing is we're moving charge around inside the material a little bit. We're not adding or removing any charge from the material. So when a neutral object is polarized, the charge moves around a bit, but the object remains neutral. And we can confirm that. Okay, so if we were to calculate the total bound charge, what would we do? We would say we would take the surface charge and we'd integrate over the surface area of whatever that volume is. And then we would add to it the volume charge density. I'll put a B here, integrated over the entire volume. All right. So this is P dot n hat dA minus, because the bound charge density was minus the gradient of the polarization. Okay, down. Okay, so what I'm going to do is I'm going to combine this to be dA again. And let's see, this is going to be the integral of P dot dA minus, what are we going to do with this? What does that remind you of? Divergence theorem, right? So we can take the volume integral of a divergence and we can write that as the surface integral of P. And of course, these two are exactly the same now. And we end up 0. That's what we wanted. Okay. Perfect. So this next topic, this next section, I think is sort of the heart of this chapter, and it's the electric displacement.
Related to this.
No, it's unfortunate. Like we talked about displacement current the other day, this JD, which was proportional to the derivative of the electric field with respect to time. We called that displacement current. It's not the same as this displacement, electric displacement. It's just an unfortunate set of terms. Okay, so we can now find the total electric field. So what we've been talking about is some external field polarizes the object, and then that polarized object makes its own electric field. So what's the combination of the two? What's the net electric field after our object has been polarized? So we have the contribution that causes the polarization. In the first place, in addition to the electric field due to the polarization itself. All right, now it could be even more complicated. We could have our insulator inside some external electric field, and the insulator itself could be charged. So not only does it have
some bound charge associated with this polarization. It has like actual extra additional electrons distributed throughout the volume or something like that. So the object may be charged. And in this case, the total charge density rho is due to 1, the bound charge, okay, rho B, and 2, for lack of a better term, they call it the free charge. But this free charge just means any charge that's not associated with the polarization. So actual physical charge that's added to this material in some way. And the free charge, which we're going to call rho F, and rho F is any charge that's not associated with the polarization. Okay, so if we accept that definition, the total charge density is the bound charge plus the free charge density. And so what we're going to do is we're going to go and we're going to start with Gauss's law. So let's start with Gauss's law. And this is not a long derivation, actually. It's pretty quick. So Gauss's law says that the divergence of E is equal to rho over epsilon naught. And so all we're going to do is we're going to say, therefore, epsilon naught times the divergence of E is the total charge density, which is the bound charge density plus the free charge density. But the bound charge density, we've already said, is minus the divergence of the polarization. Because we have the divergence on both sides, it's traditional to combine those two terms. And so therefore, if we move this to the other side, we could say the divergence of epsilon naught times E plus the polarization is equal to this rho F. You could see if the polarization is 0, then we recover the original Gauss's law. We just divide by epsilon naught, and we could drop the subscript if we wanted to for the free charge. This quantity in the brackets is defined as D, and that is what's called the electric displacement. And so we wrote down Gauss's law, or sorry, we wrote down all of Maxwell's equations last week. And we said we had this kind of qualifying statement that these are Maxwell's equations outside of matter. This is the correction to Maxwell's first equation, Gauss's law, for fields inside materials. And so therefore, the divergence of D is equal to rho F. And if we wanted to, we could integrate both sides over some volume. We could apply the divergence theorem, and we could write down an integral form of this equation, and it would look just similar to Gauss's law in free space. The only difference is we don't have to divide by epsilon naught.
Okay, and so. So this is Gauss's law for polarized materials, matter. All right, so let's do a little example to see how this works. So example. We're going to have a thin, long wire that has some charge per unit length. So we have a thin wire with charge per unit length lambda that is surrounded by a, let's say, by rubber insulation of radius A. And so the question is to find D, this electric displacement. All right, so here's our wire. This has charge per unit length lambda, and we're going to surround it by this piece of rubber. I'll draw just a section of it, and this has radius A. There's really mathematically all the tools that we've already been using, we just continue to use them. So we're going to basically start with this revised version of Gauss's law. And the nice thing about this is that we don't have to calculate the bound charge if we don't want to, because this Gauss's law depends only on the free charge, which is associated with the charge per unit length lambda of this charged wire. And we do all of the same stuff. So we start with a Gaussian surface. So this is our Gaussian surface. And we say, okay, we're going to work in cylindrical coordinates. And so we'll say that is radius S. And well, if our Gaussian surface has length L, how much charge is inside our Gaussian surface of length L if our wire has charge per unit length lambda? Yeah, it's just lambda L. That's all. So this is just equal to lambda L. Before we move on, I could have chosen my Gaussian surface to have some radius S that was bigger than A. If I did that, I would still say that my free charge is still lambda times L. Nothing changes. Maybe there's bound charge on the surface of this rubber cylinder, but there's nothing in here that explicitly depends on that bound charge. So whether I'm inside or outside the rubber, I have exactly the same thing for this free charge. Okay, and so the usual sort of Gauss's law type stuff, we would d 4 pi epsilon naught, sorry, no, what am I doing? I don't have a sphere, I have a cylinder. And so the area, the surface area of that cylinder is going to be 2 pi s times the length. We cancel the length, and we would say, therefore, d is equal to lambda over 2 pi s. And if we want to, we could put in some vector notation. And so this is valid inside and outside our rubber. So in fact, we would say E times epsilon naught plus the polarization is our electric displacement, 2 pi s, s hat. We can't really go any further unless we somehow knew something about this polarization. If I wanted to ask about the electric field inside the rubber. To find E inside the rubber, we would need to know P. On Wednesday, we'll talk about linear dielectrics, in which the polarization is proportional to the electric field. And then in that case, we can make some progress. But until then, someone would have to tell us the polarization in order to go further. However, outside the rubber, right, the polarization is a property of the material. So once we go outside that material, this P will be equal to 0. We know P is equal to 0, and therefore E outside. Well, let's see. We say P is equal to 0, we divide by epsilon naught, and this would just be lambda over 2 pi epsilon naught S hat. And so this is for S greater than A. And you might recognize that this is the exact same solution that you get whether or not the dielectric piece of rubber is there. And it has to be the case because Gauss's law, the original Gauss's law, says that E dot dA integrated is equal to Q closed over epsilon naught. And even if our rubber is polarized, for a Gaussian surface outside that rubber, all we care about is the total charge inside. So if it's polarized, then there's some surface charge on the outer surface. There's going to be some corresponding surface charge on the inner surface right beside that wire that cancels that total bound charge. And so the electric field outside is not changed. It's only inside the polarized material where we see the change. Okay, good. So let's just make a couple of notes here. So note that D is not an exact parallel of the electric field. And we can see that fairly easily. So for example, we could consider the curl of D. Well, that's going to be the curl of epsilon naught E plus the polarization. So that's epsilon naught curl of E plus the curl of P. Now in electrostatics, the curl of E is what? 0. So this is 0 in electrostatics. Right, we since revised that with the curl of E is equal to minus T into T if we have changing fields. But in electrostatics, it was equal to 0. But there's no reason to expect that the curl of the polarization is 0. In fact, it often is not the case that it's 0. And so we see that the curl of D is not 0, which means that it's not an exact parallel to the electric field. So in general, the curl of P is not 0, and therefore the curl of D is not equal to 0. And what that means is what the curl of E equal to 0 allowed us to do was to write a scalar potential for the electric field. So there is no corresponding scalar potential for the electric displacement. So there's no scalar potential for D. Okay, I think what we'll do is we'll write down the boundary conditions for the electric displacement, and then we'll do one more example. So the corresponding, well, here, let me remind you what the boundary conditions were. So the boundary conditions for the electric field were, okay, it was E parallel above minus E parallel below was equal to 0, or E parallel above was equal to E parallel below. And then it was, there was a discontinuity for the perpendicular components, and that had to do with the surface charge. So the difference in E perpendicular was sigma over epsilon naught. So in terms of D is epsilon naught E plus the polarization, the modified boundary conditions become D parallel above minus D parallel below is equal to, well, the electric field is going to contribute nothing to that, so it's just going to be whatever the corresponding polarization is. Now, if it was a boundary between a dielectric and free space, say like P above would be 0, but you could have like a sandwich of dielectrics, like you could have one dielectric and then another one on top, and they could have different polarizations at that boundary. Okay, and then D perpendicular above minus D perpendicular below is equal to sigma free. So we'll just, we get rid of the epsilon naught, and then we put our little subscript free to distinguish it from that bound charge. All right. So let's do one more example, and we'll see how we can apply some of this if we're given an actual expression for the polarization. So a thick spherical dielectric shell has a frozen in polarization. So somehow we have some material that has a polarization K over R hat. So what frozen in means is that somehow we have this polarization even when this dielectric is not in some external electric field. And so the question is, find E in the regions okay, so there could be the following. Here, I'll draw the picture and these will make more sense in a second. So we have a thick dielectric spherical shell. We're going to say that the inner radius is A and the outer radius is B, and this is our dielectric is shaded blue. Okay, so, well, what we could do is we could go with our modified Gauss's law in integral form. If our dielectric is uncharged, then sigma free would be 0. Sorry, why did I write sigma free? This should just be, yeah, it should be Q free. This is wrong. Q free enclosed. All right, so if the dielectric is uncharged, then Q free is equal to 0. And so in all regions, we'd have that d dot dA, which would be, so this time I have a sphere, right? So if I was to draw a Gaussian surface, it doesn't matter really where I draw it. I'll draw it inside the dielectric. The surface area of my Gaussian surface is going to be 4 pi r squared. And so this is going to be equal to d times 4 pi r squared. And this is true for all 3 regions. So I don't have to keep repeating that. Okay. But d is epsilon naught E plus P pi r squared. All right. So let's do region R is less than A. So we're inside the dielectric. So here, we're inside the cavity of our dielectric, where P is equal to 0. This has to be equal to 0 because we said free charge is 0. Well, if P is 0, then what's E going to be? Yeah, epsilon naught E plus 0 is equal to 0. I can divide by the 4 pi r squared. It doesn't matter. It's just 0, right? Okay. Let's say R is bigger than B. So this is outside the dielectric, where P is also equal to 0. And we're going to find E equals 0 again. So last, we are in this region. And so we would say epsilon naught E plus P times 4 pi r squared. The 4 pi r squared really doesn't matter at all in this case, because I can just divide by the 4 pi r squared. And we say, therefore, epsilon naught E is equal to minus P, or E is equal to minus P over epsilon naught. But we were given this polarization, I think. Yeah, it was K over R in the R hat direction. And so therefore, E is equal to minus K over epsilon naught R in the R hat direction. And this is true for R inside the actual dielectric material. Notice again that this electric field is opposite the direction of the polarization. That negative sign emerges. The only other thing I'll say is that we could repeat this problem and find the exact same results using an analysis of the bound charges. Okay, so we could repeat this calculation using the bound charges. I won't do it, but I'll set some of it up for you. Okay, so there's our dielectric. What we're going to have to do is we're going to have to calculate the bound surface charge density on the inside and outside surfaces. So we could say sigma B, let's say outside, well, okay. Sigma B outside is going to be equal to what? It's P dot N hat. But in our case, P was what? It was K over R hat. And for outside, the N hat is in the radial direction. So it's dot R hat. It's just going to be K over R. Okay, so sigma B inside will be P dot N hat, which will be K over R hat dotted with minus R hat, and that's pointing inwards in this case. And so that's going to be minus K over R. And this is an example where the volume charge density, the bound volume charge density is not going to be 0. Rho B is minus the divergence of P, which is going to be minus d by dr of K over R. And let's see, we take the R derivative, we're going to get minus 1 over R squared. It's going to cancel with that minus sign. I think, why did, I think I have a sign issue here, but I can't see it right now. But I think this is going to be plus K over R squared for this region. Now, we could do very quickly the electric field that would be inside. Well, there's no polarization, there's no bound charge or anything like that. So if you just did Gauss's law on the inside, you're going to get E is equal to 0. What are you going to get for Gauss's law along the outside? What's Q enclosed going to be? Well, yeah, it would have contributions from rho here, and it would have 2 contributions from these sigmas. What's the total? What's the total going to be? What did we say about when we polarize an object, we move charge around, but we're not adding any actual charge to or removing any actual charge from the material? 0. So if you found the total charge here, it's still going to be 0, and the electric field is still going to be 0 outside. The only thing that's going to change is that when you do Gauss's law here, what you're going to have is you're going to have some bound charge on this inside surface, and you're going to have a contribution from the charge density out to this orange line. And if you do Gauss's law properly, you will get exactly the same answer that we calculated here. Okay, and so you can take either one of those approaches to find those results. All right, so what we'll do next time is we'll do some more practical sort of examples, like actually how do you change when you put a dielectric in between the plates of a capacitor? How does the capacitance change? What is the force on a dielectric when it's entering an electric field? Things like that. Okay, good. So thank you very much. We will see you on Wednesday. Thank you for your assignments. I'll try to not forget. All right. Oh, sorry. I'm confused. Sorry. I'm returning assignments. I got confused. I just got out of a different class where I did collect assignments. Yeah. Sorry. No. Yeah. So, all right. What I should say is that the assignment 5 has been posted. So that's what I can say.